reset change. Yeah. So to reset the change
it's the change because you're not disclosing it.
Okay, for those students who are actually from the previous class, please leave the room, okay? Okay, so let's start the lecture. So last time we talked about a few unique ways to process a query in OLAP server. So the general idea is that we create specialized index, and basically we can use bitmap trying to index tuples in the dimension table or in the fact table. Depending on whether you index the dimension table directly or you index the join the results between a dimension table and the fact table, and this way you can directly index into the fact table. And we also talk about just in case the selection condition is kind of strange or kind of beyond the capacity of your pre-built index, what you can always do is that you can actually do something called a star join. Again, it's not always the best way, but in many cases, it's usually the best way to execute a query, simply because the fact table is too large. Okay, so you can't afford the cost to join a huge or gigantic table with a reasonably sized table. This alone needs actually scanning the whole things again once. And if the result is still very large, then essentially you need to scan the temporary result again. I mean, a substantial amount of tuples are still in the temporary results, and you need to scan it again. So it's going to be very expensive. So the alternative idea, which is called a star join, is that we actually try to, so basically we look at this kind of options where we try to do the selection on time, do the selection on customer, and do the selection on location. And provided that each of them actually have only limited number of tuples, and we don't have too many of them together, we can afford to do the Cartesian product, or in other words, called cross join. And once you get the results, you actually only need to scan the gigantic fact table once by looking for the foreign key values. Actually, there are combinations that actually are actually allowed. Okay, so essentially, what you do is that you got this table, and provided that you can fit it in the main memory, as we calculated last time, under reasonable assumptions, it's only going to cost you, let's say, tens of megabytes, or even 100 megabytes, or even 1 gigabyte. It's okay, right? As long as it saves the cost of repeatedly visiting a large number of tuples on the disk. Okay, so that's the main idea. So the last result, if you like, is similar, again, very similar to the relational database in the sense that even if that's going to be very expensive, what should we do? So the general idea is that if you look at this query, this query actually says find the total sales per customer type in our store in Europe. So the general idea is that basically the only selection condition which help you to remove some of the irrelevant data is to say, okay, the stores in Europe. This assuming that the multinational company actually have business in 4 regions, okay, and they have approximately equal amount of transactions. Then essentially you get rid of 75% of the data, okay, but you still need to deal with 25% of the transactions in the huge fact table. And you do the aggregation, do the group by, and present the results. Okay, the result itself could be very small because essentially this is per customer type. So you can imagine that in the, I think if you go back to the table, customer type have only retail and wholesale. You might have a few, but it's going to be very small. And for our stores in Europe, actually you don't need to go through the stores. So the result is going to be very small. So you are going to see that for retail, a total number, and for wholesale, another number. Okay? So this is actually a very typical kind of aggregation query. Aggregation query means you need to crunch through a large number of data, and at the end of the day, you actually get only some very tiny amount of data come back. These data, but the final number actually depends on each and every data you actually need to deal with. Okay, if you miss some of the tuples, that number will actually be affected. Okay, it's not like, for example, if you want to find let's say the maximum in terms of each transaction have a dollar sold, right? Dollar amount. If you just want to find the maximum, things are much easier because sort of the maximum only depends on. I mean, you can argue that there are clever ways to get rid of a lot of other data. But for sum or for average or these kind of things, essentially each and every piece of data which satisfies the query condition affects the final results. Okay, so if you can't afford to do approximate query processing, if you really want the exact number, you have to go through a lot of data. So in this case, this kind of aggregation are still very expensive. It results into very long response time. Very long response time. So the last result we actually have is to actually do some kind of pre-computation. Okay, so it turns out that because of the way we actually model data in multi-dimensional model, most of the aggregations are actually you can see that you can actually answer it from one of the aggregated data cube. So if you remember, in the entire data cube, we actually have a lattice. We actually have a lattice. It's way back. We have something like this kind of lattice. So the previous query, if I remember correctly, it's customer. So we don't have customer here. Let's say it's actually by different product type. Okay, we don't have product type here. But you can imagine that essentially the previous query is actually related to this cube. Okay, for example, if I want to find all the cells related to, if I don't have any condition, if I just want to find total sales according to different product type. Let's say this is not detailed product, it's product type. Then basically I can, if I pre-compute this cuboid, again, this cuboid is actually literally corresponding to one of the colored, cells. I mean, in this picture. So then we don't really need to go through the base cuboid. So this is the base cuboid. It contains everything. But in order to find the answer, you need to go through a lot of them. Okay? But for this one, this is much smaller, and you can directly find the answer. Okay? So what if, for example, as we said, okay, we just pretend, okay, this is not country. Instead of this is not country, but instead this is a region. Okay, so let's say if we are only interested in the total sale per product type in Europe only. So what you do is that you actually find a data cube which is here, right? Essentially, you actually find the data cube which is this one. Which is this one, and this one actually contains again the region, read country as region, and sorry, not this one. Should be country and product. Should again the name you should think about. So think about this as product type, and this is actually region. And this will actually be the product type, and this is actually region, okay, instead of store, okay. Basically, if you look at this cube, this cube actually have two attributes. Two dimensions. One is actually product type. At the product type level. Basically, it's the product dimension, and the other one is store dimension, but at the region level. So in there, you can actually look at only the, you only need to do a selection on this cube to keep all the tuples related to Europe, and assume that there are two product types or whatever. Basically, you are left with two numbers, and that's actually exactly your answer. Okay? So the general idea is that if we can pre-compute all these kind of things, then we can answer a lot of complex queries. Okay, that's our last result. But remember, when we actually look at this one, we actually mentioned that in low-dimensional case, the white part, which is the base cube grid, versus the entire collection of cube grids, which is the entire cube, is actually not too different. Maybe it's several times larger, but if the dimension is actually high, basically the entire cube, which contains all the small cubes here, if you really pre-compute it and store it on the disk, it's going to take a large amount of space. Okay? In large cases, it could be, let's say, hundreds times of the base data. Okay? So in the early days, what we do is that we actually do something called so by the way, this is actually in relation database. This is actually called a material. So not this one. This one is the basic one. So you definitely have this one. So let's say for this one, we actually can call it materialized view. Okay. So basically, essentially, it means materialized table. Okay. So what we do is that among all these kind of things, we only select small amount of cube grid, which are actually beneficial to our workload, and it's also within the space budget. Okay, so there are actually work to do that, and there are even further work where it says, okay, I don't really need to materialize the entire cube grid. For example, if most of the query is, because if you really have sales by different country, there are sales there are small countries where the total amount of sales is actually much smaller than some of the big cities, countries. So basically, you can actually, even for each of the cube grid, you can actually selectively materialize part of it. Okay, but there are lots of different schemes. Okay, so we won't go down into that path. We just assume that in certain scenarios, you are able to actually store all the cube grids. Okay, so the general idea is that we actually give you these kind of things, the base cube grid, and I want a way to quickly compute all the other derived cube grids, and they form a complete cube. Okay, so as long as we can do that fast, basically we can actually, and the space allowing, we can actually store all of them, and when do the query processing, it will be much easier. So that's the high-level idea. Let's come back. Yeah, so essentially this is what I meant here. So just assume that you actually materialize the cube grid, which is year, type, and city. all you need to do is to do a selection on this one. And this one is actually much smaller because for year, let's say you have 10 different years, right? For type, again, this is the customer. I think there are only 2 types. And the city, let's say even if you have 5,000 cities, you do the computation, the whole qubit is actually small. Okay, you can actually, then you do selection, even if you do a simple scan over each and every tuple and do the selection, then you do the group by, that's going to be much cheaper. Okay, so that's the idea. As I said, I mean, you can materialize all of them, or you can materialize some of them. Actually, this is actually, whenever you can only materialize some of them, that's usually the job of DBA or performance. DBA to look into all the constraints you have and what kind of workload you have, and the frequency and so on and so forth, trying to determine the best way. It's actually called a physical organization, so physical configuration. So we actually talk about 2 related issues. The first one is how to store the materialized qubits. So it turns out that for ROLAP, again, this is actually, we talk about at the physical level. If you use relational database to do that, what's the way? Okay, and later you will see that in MOLAP, in the multidimensional implementation, they have another way to store all the qubits. Okay, and the second way to how to compute them efficiently. So what's the naive idea to answer the first one in a relational database is that if you remember, I'm just going to use ABC as dimensions. I won't write the name. So if you think about the lattice actually looks like this. Okay, this should be BC. This is AC. It doesn't matter. It just changed the look. And then you have A, B, C. You just need to be careful to link them in the right order. And you have, this is an empty set. Empty set actually means that's a 0-dimensional cube. Right. So the naive idea is that if you look at this qubit, okay, it actually have how many attributes you have, because we are going to store it in the relational database. So it's going to have 4 attributes. Just assume that we have only one measure, okay, just to keep things simple. So these 3 are going to be the dimensions, right? Essentially, that's going to be the foreign key into the particular. For example, there is a table for dimension A, dimension table for dimension A, and so on and so forth. And this is essentially the fact table. So basically, it contains the foreign key to A, B, C, and essentially you have, usually I write M as the measure. Okay. If you have more than one measure, then basically it's going to have even more attributes. But the bottom line is that if you have 3-dimensional cube, you are looking at at least 4 attributes. And for this one, you actually have 3 attributes. So you have 4 attributes here, again, because you have a measure. Okay, if there is no measure, there is no point to create this kind of qubit. Right? You just list all the possibilities, or there are different ways to interpret that, but basically there is no valuable information associated with it. So basically, you need to create a table for AB, and even though AC also have 3 attributes, right? You can't reuse the same table as AB because semantically it's different. Okay, if you mix all of them together, it's going to be very hard for you to figure out, okay, which tuple actually belong to AB, which tuple belong to AC. Especially if you think about all of the A values and the B values, they are foreign keys. Foreign keys are usually some kind of binary data. So there is no way you can figure out basically this is foreign key to C or foreign key to B. Of course, you can do the join and you can find that out. But again, this is very expensive, right? So the naive solution that if you have 3-dimensional case, the total number of qubit is 2 to the power of 3. So if you have d dimension, it's going to be 2 to the power of d. So in real scenarios, 10-dimensional cube is very common. So you are going to looking at more than 1,000 tables, okay, each one for one particular cubic. Then, if you think about the good thing about this design is that each table is on its own, but then it's going to be very messy. Just think about naming it, and if you want to do some kind of query, right, you need to have a way to encode, give it a whatever name, so that you can select from this table, right? If you say just table 1 to table 2 or table 1024, that's not going to easily tell you what kind of attributes there are in the table. So that's why Jim Gray actually, as I said, I mean, he is one of the Turing Award winner, actually proposed the cube-by idea and also a physical storage scheme for the entire data cube in the relational database. So his idea is actually very simple. Just use one more special keyword or whatever. It's very similar to the now, right? In the relational database, if, let's say, phone number, okay, whenever you insert a customer, just in case you don't know his or her phone number, you don't need to enter anything into that in your insertion, and the database will actually store a special value, which is called a now. And if you still recall, whenever you do for example, if you want to find all the customer with missing phone information, you can't say, okay, phone equals now. There is a special way to, it's actually called is now or is not now. Okay, but this actually shows that databases are already using this kind of special value to handle some of the tricky issues in real life. So all they need to do is to have one more special value, which is called or. And with that, you can actually see the dashed line is actually not very aligned with this one, but you can actually see that we have this one corresponding to the cube of AB. Let's say store is A, product is actually B, right? So all of the tuples above this line actually have both store information and the product information, and with the sum amount is our measure. Okay, usually I write as M. So this part is actually A up to here, and this part is actually B, and this is actually our empty cubic. Okay. The good thing that at least we have a clever way to store them. So you only need one table, and the other benefit is that just imagine that you, for whatever reason, for time reason or for space reason, let's say currently you didn't materialize the cubic A. So you do have this is the base cubic. You definitely need to have them, right? And then you actually are able to materialize B and C, B and empty cubic B and cubic nothing, which is all, okay? Then this is still in one table, right? Okay? But later, if you find time or a space allows you to actually materialize this A, you just add them, okay? Again, this is a table, so logically, I mean, physically, they might all the tuples in the same cubic are not necessarily clustered together. But anyway, I mean, logically, you can actually think they are actually group up together. Okay, and even better, they actually create a new keyword, again to extend to SQL. Say, okay, cube by. So by using this cube by keyword, they will actually. So cube by is actually a generalization of the group by. Okay, so if you do the group by, it's only going to give you this AB, and if you do the cube by, it actually cube by actually are followed by a sequence of attributes. Actually dimension here, but in the star schema, it's basically those are the attributes, and they will actually give you all the group bys, all the possible group bys, right? So basically, if you do cube by of A, comma B, basically they will actually give you 4 different group bys. Okay. So that's how you actually store and actually just use a ordinary SQL statement. You can create the entire cube. I think there are. I remember in the early days, I mean, in IBM syntax, they actually allow you to say, create all the cubrates which includes dimension A. I forgot the syntax, but basically you can actually cube by with certain, I think they have a combination of roll-up keywords and whatever. So basically you can actually say, okay, I only materialize some of the cubrates. Okay, and everything can be done in a declarative manner. So now we move on to the second question. How do we just assume that user really issued a cube by statement, which by default actually compute all the cubrates? How are we going to do this efficiently? So again, look at this lattice. So this lattice is the most important one. What we observe is that if you look at a kubrate AB, again, just think about this is A, B, C. And look at kubrate A. Okay, so the kubrate AB, I mean, the actual content doesn't matter. It just give you some kind of concrete example to understand what's going on. So in the kubrate AB, it actually have detailed A values and B values. Basically, they are a combination and the corresponding measure, the corresponding total sales, right? And for kubrate A, it only have all the unique A values and the corresponding aggregates. So it turns out that this value, right, is related to these four values, right? Because in the kubrate AB, these are the only four values where the A dimension actually equal to 1. And if you want to calculate for this tuple says, okay, I want to know the total aggregate value for the case where A equal to 1. And the B is or, you can think about B is, I don't care. Okay, it can be any value. So B can be any value, it doesn't matter, right? Sometimes or I actually write it as star, which is also very intuitive. So basically what you need to do is that you need to aggregate them. And by default, we use sum. So if you add them together, that's going to be 100. Okay, and the second tuple is going to be just 50. Right. And you can actually verify that from this one, you can also compute kubrate B. Okay, so the general idea is that whenever I'm going to compute kubrate A, I can actually compute it from kubrate AB. Of course, I can also compute it from kubrate ABC. Right? You can actually convince yourself is that for any, I mean, it can be computed from any kubrate for this kubrate A, as long as there is a kubrate which contains A and something else. You can actually compute this kubrate A from that kubrate. So it includes AB, AC, ABC in the three-dimensional example. So what we can do is that, so this naturally gives us something called the top-down approach. It's top-down because the computation order is actually, we want to calculate this one, or if this is the base kubrate, there is no calculation. It's just the fact table in the star schema. And then what you do is that you can actually calculate this one, and this one, and this one. And then whenever you calculate, for example, this quarter, you can actually choose, because this one can be computed from, computed from either this guy and this guy, right? These two starred kubrate. And because both of them have already been computed. So naturally, you actually want to compute this quarter from the one which is smaller, right? Or, I mean, in database, they actually can do some kind of estimation on what's the cost of computing this one, essentially a further group by from this kubrate versus from this one, and they can always choose the best strategy. Okay, so this is actually a very natural approach called top-down approach, and there are actually lots of sophisticated algorithms. But they all follow the idea that you need to compute, you need to start from the fine granularity kubrate then gradually do the aggregation, because each and every cuboid at the bottom is more at the cost granularity, because you get rid of some of the dimensions. Okay, so it seems like this is very natural, and you can convince yourself that if you calculate cuboid A first, right? Can you calculate cuboid AB? You can't. The cuboid A is highly aggregated information, and during this process, you actually, all the information lost is lost. You only know this is 100, but you can't know, okay, this 100 is contributed by a different B values. Actually, you have BB. Again, this is just for illustrating the example. So the general idea that nobody will actually think about, okay, I can compute A first, then compute cuboid AB. But it turns out that the next algorithm we are going to talk about, which is one of the actually very elegant, but if you are if you are not familiar with recursion or some notion related to recursion, it's going to be pretty hard at the beginning for you to understand. Okay, but what they do is that they actually do it bottom up. It's called bottom up cubing, and by the nature, you can imagine that they actually calculate from bottom really to the up. Okay, so let's see how they work. Actually, when I was doing my PhD, we actually implemented this algorithm. I can tell you that for this top-down approach, the best paper was in 1998. So this was proposed in 1999. So we implement the VLDB 1998 paper. It takes maybe 4,000 lines of code in C, in C++. Basically, in this one, it's something like 500 lines of code, okay, including the I/O part, because we also need to store it on the disk or whatever, reading the file or whatever. It's very simple to implement, but it's really fast. And also there are additional optimization you can do, which make it even more appealing. Okay, so the original paper, this kind of figure actually comes from the original paper. And the actual algorithm is going to be slightly different from what we are going to introduce. We are going to introduce a simpler version, which is much easier to understand. And once you understand this version, and if you are interested, you can go back to the research paper, and in the textbook, they also give the details. But again, we only require you to understand the simple recursive version. So that's why I call it BOCSR. Okay, so simple recursion version. Their actual version is more refined, but it's a little bit harder to understand. But once you understand this one, with some effort, you can understand the actual version they do. Okay? So before that, we actually need to look at recursion. Okay? So recursion is actually very powerful techniques, and we are going to see it in several places throughout the course. I think the simplest recursion is actually the one-dimensional version, which is the, there are actually two famous examples. One is actually the factorial. Okay, so again, depending on how you define, factorial, one of the definitions is to say, okay, n, let's say this is actually factorial of n, right? You can think about, let's say this is actually f of n. F is function. The function stands for factorial function for now. That's going to be one of the way to say is that n times n minus 1 times blah, 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 all the way to 1. And there are n numbers. Right? That's a way to do the definition. But again, it's ugly, right? It actually assumes that people can figure out, okay, what the dot parts actually means. And also, if you look at more advanced mathematics, you seldom define things in this kind of, this is actually not a rigorous way to do the definition, okay? Just to put it in this way. So a better way is to define it recursively, which is also very simple, right? So the general idea that the factorial of n is actually the factorial n minus 1 times n. Okay? So basically, you will see that it translates directly into this kind of things. But it's actually much better. Okay? So in this definition, you can actually see that this Fn can be generalized to, so you actually know what is what is 3.5 factorial. Again, I don't need the value, right? But you know that it's going to be 2.5 times what?
3.5.
Yeah, 3.5. Okay? So as long as I know this one, I can do the calculation. And if you boil down all the way to, probably, if we limit everything to be positive, non-negative number, as long as I can define what is f 0.5. Okay? So anyone know how to define fraction number factorial? It's actually related to gamma function. So if you're interested, you can look up gamma function. But anyway, I mean, but you see the thing. This is also related to the linear algebra. As I said, I mean, the property is more important. Okay, the factorial, I mean, both the integer version and the floating version actually capture the important property that it's like this. Okay, just like this formula shows. But again, these kind of things, you need to define something. This is usually I call it a boundary condition. Some of the book actually says base case or boundary case or boundary condition or base case. Anyway, the name doesn't really matter too much. But this actually is more like a stop line. Okay. So basically, whenever, because otherwise, I mean, this will goes on and on and on and on. It never stops. So it's almost like it looks very good, but it's like always chasing its, I mean, like a dog chasing its tails. You never get anything useful out of it. So you need to have a boundary condition, say, okay, at the end of the day, you are going to reach this step, and I define what this value is. Okay. In fact, once you understand this one, even for n equal to 1, you can define this to be, let's say, 3.5. Then you have your own version of factorial. Maybe you should use another name, right? But anyway, it doesn't matter, okay, to some extent. So we use the common definition where fn equal to 1, right? Okay, so you can see that this kind of recursive definition is actually very common in mathematics. Okay, in terms of computation, there are actually ways that we can actually make it faster. Okay, but we are not going to delve too much into it. But try to understand that whenever you want to do something trickier, you can actually define. You can actually, especially the parameter is actually totally ordered set. Okay, you can actually do this for partially ordered set as well. But all the integers are actually totally ordered. Then you can actually do the definition in a recursive way. So another example is Fibonacci series, which is actually n equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. Right, so the series actually goes like 1, 1, 2, 1 plus this is 3, this is 5, this is 8, this is 13, and so on and so forth, right? So this is a Fibonacci series. So, for example, if I ask you to calculate the n's Fibonacci series number, do you know how to do that? So the naive way is really to use this formula, right? To say, okay, if I want to do fib of 12, I need to work out what is fib of 11 and the fib of 10, and so on and so forth. But we probably, I think the simple version is that you know that you can actually order the computation starting from the smaller one to the larger one. And you only need to fill in this table up to the, let's say this is 12th entry, and you get a number, right? Okay, but what if this number is not 12? Let's say this is 1, 2, 3, 4, 5, 6, 7. Okay. In fact, this Fibonacci series is actually related to you can actually calculate this using exponential exponent functions. Okay, so basically you can calculate this one much faster. Basically, in terms of complexity, instead of doing it linearly, so let's say this is nth entry, instead of doing O(n), you actually can do O log n. Okay, but anyway, I mean, so so my point is that the definition is actually can be made very simple, but the calculation could be there are a bunch of techniques that you can use to speed it up. Okay, another example is quicksort. Quicksort means I give you an array and ask you to sort all the, let's say, integers. Okay, it does not necessarily need to be integers into, let's say, increasing order of numbers, and just assume that there is no duplicates. It doesn't really matter, but just to keep things simple. So what's going on is that, of course, you can think about a very delicate, let's say, insertion sort, bubble sort, heap sort, whatever. But quicksort, and it's a very similar version. It's called a merge sort. It's actually very simple. Okay, and it can be described very concisely using recursion. So quicksort actually means I'm going to sort a very long array. Let's say x1 to xn, right? I don't know how to do that. Okay, let's say, can we break down the problem into smaller problems? And I can call this same procedure to solve the smaller problems, and then doing some kind of combination or doing some kind of post-processing, I can get the answer for the original one. It's almost like you get a job to, let's say, build a complex program. Okay, you need to have a front end and a back end, right? So if you are really clear about what's going on, you can actually define the interface and say, okay, the front end should do whatever things, and back end need to do whatever things, and you can delegate it to other people, and as long as they've completed their job, you actually put them together, right? It's not exactly like this one. It's almost like you delegate, you decompose into a small task, and you delegate it to yourself. But think about that's delegated to someone else. So basically, this actually means that I can select any number as the so-called pivot in this array. You can pick any number. Of course, I mean, there are clever ways you can do to make sure that on average it's actually going to be very good. But yeah, that's the data structure and algorithm course. So basically, if you pick the pivots, we can actually split the original array always into two parts. One is called y's and the other called z's. Basically, y's are all the number which is smaller or equal to pivot. Right? This is always doable. And these are the rest of them. So the general idea that once you have chosen the pivots, again, I'm not talking about the efficient implementation. The naive implementation that you actually, let's say, randomly pick one, and then you go through all the x1 to xn, and whenever you process one of the elements, based on the comparison with you just remember what the pivot value is, you actually move it to the left-hand side or right-hand side. Right? So naturally, they become two arrays, which is ys and zs. And then all you need to do is to sort both array using exactly the same thing recursively. And finally, this double plus actually means concatenate them together. And by design, we know that any number, any y from ys, is going to be smaller or equal to any z from zs. Right? Just by the nature of the definition of ys and zs. Okay, so the problem is solved. Finally, you need to define the boundary condition. If you keep on dividing a longer array into smaller one and smaller one, eventually you can define, okay, empty case, or in many cases you can define, like, let's say, only one single element. And whenever it's a single element and you want to do the sorting, there is nothing you need to do. You just return it. Okay? So you can see that this is the general pattern of divide and conquer and the recursion. Basically, you divide the problem into smaller problems, and using the same procedure. I mean, if you do recursion, you use the same procedure to solve it, and finally you do some kind of post-processing. Usually very, very cheap. And then finally you think about, okay, what are the trivial case, because you keep dividing the problem into smaller and smaller size, eventually it becomes a trivial problem. Okay, anybody can solve it, and then you make sure you solve it correctly, and everything works. Okay, you don't really need to. I mean, if you don't care about the efficiency, you don't really need to worry about how the computer actually schedule the computation. but that's the whole thing. So these are actually the recursion. With that, we can actually talk about the algorithm. But before that, we actually talk about another understanding of recursion. This is also important. One of the things I suggest you to do is that try to gain deeper understanding. So for many things, if you understand in one way, try to understand in another way. So sometimes both ways, or even more than one ways, actually help you in certain scenario. Okay, so this is similar to recursion, but we actually look at another property of this kind of recursive algorithm. Oh, by the way, if you look at this sorting, right? Sorting is a non-trivial example. If I want you to prove the sorting procedure, this algorithm, this recursive algorithm is correct. You probably have never thought about that. Actually, there are people in software. So basically, there are a bunch of computer science. They actually try to verify your program actually is correct. Okay, it's almost like a theorem proving or whatever things. You can imagine that for high-risk systems like rockets or high-speed trains or airplanes, right? You really want to make sure that every piece of software you've written there has been verified that there is no out of index error or whatever things, right? You don't really want to, because as long as there are errors, there is a danger that many people's life will be lost. So anyway, but we don't really need those kind of very advanced knowledge. So for this kind of sorting algorithm, recursive quicksort, it's fairly easy to prove that it's correct. Okay, we won't go into the formal proof, but the general idea is that just look at the recursion. The key point is look at the recursion and to understand that this recursion makes sense. Okay, whenever it returns a sorted subarray and it returns another sorted subarray, you concat them together. First of all, the result is definitely going to be sorted, as I already argued. And then you can argue that every element, x1, must be in y's or in z's. Right? So nothing is lost, and it's definitely going to be sorted. So informally, this actually shows that this algorithm is correct. Right? Now, another way to show that the algorithm is correct is to look at this example. So this is actually, sometimes we actually write it in this way. This actually means from n balls, right? You choose, number the balls or color the balls. Basically, they are, you can distinguish them. Choose m balls, and how many different ways you can choose. Right? This is a number of combinations. Okay. So it's a fundamental thing in a number of places, right? So it turns out that this number have this property. So Cnm equal to Cn minus 1 and n minus 1 and plus this one. Okay. I think in my high school, there are a lot of mathematical problems you need to work out, and you need to use this theorem, right? So at that time, you probably just memorize it, okay, and to be able to use it in the right place. So can you understand it? So I just use a concrete example. Once you work on understand the concrete example, it's easy for you to see that for any n and m integers, that the same process actually applies, and that hence it's correct. Okay, so we are considering choose 3 balls out of 5 balls, and just for the sake of argument, each ball is actually have a unique number, A, B, C, D, E, right? Okay. Now what you do is that you pick any ball you like. Okay. For example, I like D, so I choose D. Now I'm saying that because you are going to pick 3 balls, right? I don't really need to look at your. Imagine that you actually pick 3 balls, and I don't need to look at what are the balls you have chosen. I just ask you a very simple question: does the 3 balls contain the ball D? What are the possible answers? Either yes or no, right? You can't say I don't know, right? This means you can't read the letters. Okay, so this is the general configuration whenever you say, okay, the 3 balls I have chosen contains D. This means you have already committed to D, right? This question mark 1, question mark 2 is just a notation to say, okay, these are 2 different balls. Okay, to be exact, you also need to make sure that they are actually not equal to each other. But you get the idea, okay? Just to keep everything simple. This actually means you have already committed on the ball D, and then you can choose any of the other balls from the rest of the balls, right? So what's the number? So the number of ways you can choose any of the 2 balls from the rest of the balls are going to be 4 balls, because you already committed to D. So the rest of the balls are going to A, B, C, and E. So 4 balls, you need to choose 2. Right? And the other case is that you said, okay, none of my 3 balls actually contains ball D. That's fine. That's corresponding to this case. Then each of the balls have only 4 choices. Right? And you are going to choose 3 balls, and they are not going to be equal or whatever. So that's going to be you choose 3 balls out of 4 balls. Okay, so the reason that 5 balls choose 3 definitely equal to these 2 guys are essentially based on whether you choose a particular ball or not. So this is the case of yes. This is the case of no. And you can guarantee that everything is considered, right? Okay. So the reason I actually draw this kind of cloud is actually called a solution space. Okay, this actually means all the valid solutions, which is actually choosing 3 balls from 5 balls. And by using a particular criteria, I'm dividing the solution space into left-hand side and right-hand side. And on each side, I can do the counting. And finally, and I know that, and there is no solution which belongs to both of them, right? Because if one solution belongs to both of them, it means it contains the D and it does not contain D, which is a contradiction, right? So later you will see that we can actually understand the first complex algorithm using actually both understandings. Okay, so let's have 10 minutes break, then we move on to the next one. Okay. Let's move on and think about can we use this to the cubing problem. So the cubing problem basically says, okay, I'll give you the white part, which is a base cubrid. Let's say let's start with 2 dimensions. So it contains dimension A and B. We actually need to compute all the possible way to do the group bias. That's the complete data cube. Okay. So it actually contains the cubrid A, cubrid B, and cubrid C. Cubrid nothing. Okay. So what is 2-dimensional cubrid? 2-dimensional cubrid actually can be visualized much easier. Okay. So we start with 2 dimensions. So the white part, this white part is our cubrid. So I just use a general case where you have dimension A and B, and A have 2 values, A1 and A2. B have 3 values, B1, B2, B3. Okay, so that's the base cubrid. This is cubrid AB. And if you look at the yellow part, it's just like Excel. Okay, so I didn't put it. It should be star, right? You put star here. I mean, if you look at the blue part, it's easy. It's star star, right? So that's going to be the grand total, if you like. So that's going to be the 6 values from M01 to M23 summed together. But the yellow part corresponding to the case where the value is actually like A1 and the star, right? So this one is sort of like A1 star, and let's say that the number is 100. And this is going to be A2 star, let's say 50. Again, the number doesn't really matter, right? So this gives you the idea that this yellow part is going to be the cubrid of A, and you can easily reason that the green part is cubrid of B, right? And this part is actually cubrid of nothing. Okay, if I put brackets to denote it. Okay, so so first of all, you know what's the result, right? So how do you do the aggregation? Think about Excel, right? So what we do is that we actually, I mean, if you don't know a shortcut to do that, what you do that you select the first row. You select the first row, right? Imagine you use the mouse to select the first row, and then there is a small handle on the bottom right, and you drag it to this cell, right? And I forgot whether they default to sum or whatever, but basically you can choose the aggregation function, right? By default, we choose sum, and they will automatically have this value. And what you do is, of course, you can actually drag down. I mean, but if you don't know this way, the other way is that you select these 3 guys using the mouse and do the same thing again, right? So this is actually I call it step 1. And once you have done that, you do the aggregation vertically, and finally, the green part you can actually derive it from the yellow part or the green part. But let's say we still derive it from the green part, right? Okay, so you clear. So this final step 3, the blue one, is actually coming from the green part. Okay, so that's actually what we really do in manually. Okay, and we just want to find some kind of pattern so that we can generalize this into any arbitrary dimension, because we can't easily visualize this in 3D, and for 4D it's virtually impossible. Okay. To visualize, but you still want the algorithm to operate correctly. So what we do is that we can actually use recursion. So our recursion is that we want to do a cube compute a cube, which consists of 2-dimensional case, like A and B. And by recursion, we know that the hardest part is actually both the data and the dimensions. Okay, because for example, what is a cube? If I give you the base data consists of only 1 dimension and ask you to do the cubing to compute the entire data cube, can you imagine what's going on? So imagine that you only have 1 dimension. So basically that's going to be, if I use this, actually I'd better draw it in this way. You only have A1, A2, right? That's the entirety, its entirety is actually the cubrid of A, right? That's 1-dimensional cube. So what are all the other cube-root you can derive from this one? Only this one, right? This one is empty. So one-dimensional cubing is nothing but sum them together into a new cell, right? Everybody knows how to do that. So we already established that, okay, if we can reduce problem into a 1D cubing problem, here it's only 2 cells, but we know that it doesn't matter. Even I give you 1 million cells, as long as it's 1 dimension, everybody knows how to do that. Just write a for loop, right? Okay. Now the complex thing is 2D. 2D, of course, I mean, we don't really need to do that. We know how to deal with 2D. But the thing that we want to learn a lesson such that we can generate this into any dimension, right? So in order to do that, we actually need to reduce the 2-dimensional cubing problem into a sequence of 1-dimensional problem. Just like in sorting. We are sorting a very long array. We don't know how to sort it. We break the problem into two small sorting problems. And eventually, by further doing the splitting, finally you reach a trivial case where there is only one element and there is nothing you need to do. Or you can think about, okay, you have a case. Yeah, we don't talk about efficiency, so eventually you will end up with a case with only one element. So here, so we already know that one-dimensional cubing is just given an array and compute its sum, right? So you can see that what we have already done is essentially doing that. So that's why what I said is that, so what we do in step 1, what we have done in step 1 is that we are doing a cube by for this array. And this array itself is a one-dimensional cube. Okay? And this value is going to be a cube by on this one-dimensional array. So a one right cube by. Okay, so this is actually, so in other words, you can imagine that this whole line is actually obtained by calling a one-dimensional cubing algorithm as long as you pass the white cells to the algorithm, right? And then you actually can get these two guys. Then what you do is that you actually need to get these green guys. The green guys actually corresponding to the case. You think about what this green guy means. This green guy actually means each of the value here. Let's say this is 40, this is 50, this is 90, right? And the 40 actually means the combination of A1, B1 is 40, combination of A2, B1 is 50, and the semantics of 90 is actually star B1 equals 90, right? So this one is actually star B2 and so on and so forth. So basically, what is star B2? What is star B3? What you can imagine is that we actually squash down. Okay, so you choose this dimension, right? You squash down, or like a pivoting. In the pivot operation, we already said, okay, if you want to pivot onto the dimension of B, which means you need to get rid of A. So you actually choose the A direction and squash everything into one cell. And this cell actually contains 40 and 50, right? If you squash them down. And then you apply the aggregation, this gives you 90. Okay? So after squashing, you actually have a new one-dimensional array, and then you do the 1D cubing. Okay? So that's the high-level idea. So actually, in the figure next, you actually see that we actually break down this into really like each line is just like the result of calling one-dimensional cubing algorithm, which is a straightforward aggregation. The only tricky part is the green part where we actually squash everything down into a new array. It's here it's array because it's like from 2D to 1D, okay? But in general, you actually just get rid of the first dimension, okay? So let's think about how to generate this into 3 dimensions. If we can do the same thing in 3 dimensions, we probably know that I mean there's an informal argument, but basically this should work for any dimension. So in 3 dimension, again, my drawing is not the best, but you probably can get the idea. So I only draw 2 by 2 by 2. Okay, so you can see that you have 2 values here and 2 values on A. Okay, otherwise, I mean, it's too much work in drawing. So this is so you have dimension A, dimension B, and dimension C, right? So what we do is that you can choose any dimension. Again, I choose A dimension. So what you do is that you slice these are the white cells, okay? You slice the cells according to the different A value, right? Just like we did in 2-dimensional case. So here we have 2 different A values, but even if there are 10 different A values, you got 10 slices, okay? So here you actually have 2 slices. Let's consider the top. So this is the top slice, right? So in the general position, top slice is really like a three-dimensional thing, but we know that the slice operation in data cube actually reduces dimensionality by 1. And or other words, you can actually rotate it into the right angle such that, so this is only by a rotation. Essentially, it's a 2 by 2, right? And you can see that this is actually C dimension, and this is B dimension, right? Because you slice on A. Okay, so once you get this one, what is this guy? This is a 2D cube. Okay, we just call the algorithm. Let's say the algorithm, the name is called BUC, right? So, so you just call BUC, and it's supposed once it's returned, it will actually give you something like this. The yellow part, again, I didn't distinguish the green or whatever things, but the yellow part essentially are all the aggregated values related to these 4 white cells. Okay, and this process is exactly what we did here. Okay, but we don't really need to care how they actually do that, because it's almost like a contract, right? You call this function, and as long as this function returns without error, it actually means it finished the computation. And by the contract, it should give you all the aggregation here. And you do the same thing for the bottom slice. Sorry, for the this is only for the top slice, but the bottom slice is exactly the same thing. So you actually have this guy and this guy. And again, I put them back. It looks like this guy. Okay. Again, yeah, it's really bad drawing, but it's not everything is yellow, but you get the idea. So it's like you have this one. Then if you remember, we have the green part. The green part is to squash against that chosen dimension. So what you do is that you actually, oops, yeah. So this is only the white cell. Of course, you can imagine that you already have a yellow one, but I just get rid of the yellow one for now. For the white ones, you actually squash on the A dimension, and it's going to be a 2 by 2. Again, each dimension is going to be only B and C, right? Only B and C. And the value here is going to be, let's say this is 3, this is 4, this value should be 7, right? Using sum. Okay, so you can work out these 4 different values, and then you rotate it again. It's a 3-dimensional cube, and again, I stack it on top of the previous results, and by calling the BUC on the green part only, it will actually return everything like this, which will finally be the be this part. Okay, so if you so you can actually try to take some time to understand what's going on, but essentially we are doing exactly the same thing. We start with a 3-dimensional cube, right? Our idea is that we keep on constructing 2-dimensional like base cells or cubes, and then we can pass it onto the same algorithm, which is BUC, but it only needs to deal with 2-dimensional cubing. And presumably, 2-dimensional cubing, we already know how to do that, actually through recursion as well. Okay, and once it's returned, you get the partial results, and but you also need to squash everything into another new 2-dimensional cube and do the final computation, and finally you complete your calculation. Okay, So that's the whole idea. And if you want, you can actually, so this is actually the pseudocode. Basically that's, you can look at this one and look at the operation we did in the 3-dimensional case or in 2-dimensional case. You can see the exact correspondence. Okay, so this is actually, you actually obtain for each distinct value of the first dimension, which is actually our dimension A in our example. Again, we don't consider any optimization. I mean, you can just choose the first one. But of course, if you choose a better dimension, it might be faster. Then you create a lot of slices. For each slice, you actually call the BUC on this slice and the rest of dimensions. You need to make the rest of dimension is actually the original dimension. Remove the first one. The rest is called the rest of dimensions, right? And if this is 3 dimension, you get rid of 1 dimension. The rest of dimension is 2. If this is 4, this will be 3, right? So you actually do this for each and every, if you like, horizontal slice. And finally, you do a squash. Squash is actually this project operation. You get a new d-1 dimensional base cubed kind of thing. And then you call this on this one. And again, it's a d-1 cubing. And finally, all the result together is actually everything. Okay, so this is actually done by using this kind of finding some kind of patterns or regularity, right? Another way, as I said in the recursion, another way to understand what's going on and why this algorithm is correct is really to look at what we have done and why this is always correct. So we reuse this slide. Again, we use 2-dimensional case, which is easier to explain. But actually, you can try this on 3-dimensional things. And if you can do the similar things, you probably have a correct understanding, or you deepen your understanding. So basically, if I give you, so this basic cuboid is AB, right? So imagine that what will be in the entire data cube. So if you need some kind of reminder, just look at this one. Okay, again, the number are more or whatever, but you know that all the tuple here, that's the, if you look at this table, right? This table is actually the complete data cube with all the 4 cuboids. Okay, I don't really care all the numbers here, right? But we know that all the tuple looks like all the tuple. If we look at the A dimension, it's very similar to the combination set thing. This is the ball D. Okay, so we actually look at what are the value of the tuple on the first dimension. It has to be 1. So if you look at this one, so it has to be 1, right? It could be 2. Again, I want to mark all the other things. You have 3 and 4. You have 3 and 4. And finally, you have all, right? So in other words, any tuple in the complete data cube, if you look at, you fix any dimension. By default, I can fix the first dimension. You ask what are your value, right? So your value has to be one of A dimension is store. Store actually have 4 different values in the again in the base cuboid. You don't have all, right? So you have 4 values, but we know that it can take one more value, which is all, right? Again, this extends to more general case. I mean, where the dimension have more hierarchies, there will be even more values, but the principle is the same. Okay, so we actually know that any tuple, if it's let's say 3 something something and a measure value, right? That's actually going to be our general template. Okay, so this will actually be calculated in our BUC of there are going to be a slice of 3. So if you remember in our previous algorithm, if you do the slice on each and every distinct value on, so get rid of this kind of drawing for now. We are going to do a slice slice 3, if I use this one, if you go back to the slides to see the pseudocode, slice 3 is all the base qubit. Base qubit is actually only here, where their values start with 3. Okay, so they are going to be only these two guys. Oh, sorry, the base qubit only goes to up to here. Okay, among these guys, if you actually do a slice on the distinct value on A, you definitely get a slice which is 3, right? So within this one, you actually call the BUC on this slice 3 on the rest of dimensions. Again, the rest of dimension here is B, right? And actually this is only 2-dimensional thing. So we only have, so basically this value here could be a real value, which is actually an integer, or star. But we know that what will this give me? This will give me that by passing this data, this will actually says, okay, give me the 1-dimensional cube. So the result looks like something is the B value. So it's actually, let's say you have 2 B values in this slice 3, B1 M1, B2 M2, and a star M3. That's going to be the general results by passing a, in this case, 1-dimensional array, okay? And ask you to do cubing on 1-dimension B. And the result will actually be different B's and the total for any B value, which is this one. So this will actually, so basically you can see that any value in the final data cube which starts with 3 will be computed by this recursive call. And any value which starts with star will actually be computed by the final call on the squashed data. I won't show the detail, but you actually can easily see it. Okay, so this actually convinced that any of the results in the final data cube has been computed. Nothing is lost. Okay, and also more importantly, equally importantly, every tuple, right, will only be computed once. There is no duplicates. Okay, this is a more subtle issue, but if you have duplicates, it's also very bad because in high-dimensional space, this guy will actually be computed multiple times, actually exponential in the number of dimensions. So even if you do some kind of checking to really save the computation time, but that's going to be very bad in terms of complexity. So this algorithm actually makes sure everything is computed, and everything is computed from the right place and only once. Okay, so that's the idea. So there are some kind of detailed examples, but I think you can actually. I'll probably quickly explain this. I mean, try to get rid of this one. I mean, you can start with just start with this guy. Just start with this guy and try to do the same thing by yourself. I mean, if you can figure out what's going on, you actually understand the algorithm. Okay. So what's going on is that, so remember that we are given this, so the data is actually, again, it's not well aligned. It's actually R1, R2, R3, R4, R5. Okay, it's not well aligned, but you get the idea. There are 5 tuples in the 2-dimensional cube. That's the base qubit of AB. So in other words, I write in this way, R1, R2, R5. It's a set. That's the data. By the way, the BUC actually takes 2 parameters. You take the data and take the dimensions you want to do the cubing. So as you can see that even if the data is let's say 10 dimension, you can actually choose, say, okay, I only do cube on dimension, the first and the second dimension. It's entirely okay. So you don't materialize the entire data cube, but only entire every combination of the first 2 dimensions. So you can see that this is a trivial generalization, right? So so basically you are going to do the AB cubing. So what you do is that you choose any dimension, and by default we choose A, and you do the slice, right? So A has only 2 distinct values, right? So essentially I create this first slice, I create this slice 1, and this is our slice 2. Essentially this is our slice star. Slice star is actually essentially you squash everything, right? Squash everything actually squash everything means you get rid of the first dimension. The real reason that the first dimension must be star. So that's why I use star. You can think about it, it's almost like the first dimension value is star. If you don't care about the first dimension, the B's only have 1, 2, and 3. So that's why 1, 2, and 3. And the 1's value is going to be 10 plus 20 plus 50, which is 80. Okay? So essentially, you create 3 pieces of one-dimensional data, essentially, right? And then you call the BUC on the only remaining dimension, which is B in this case. And you don't need to think about, okay, it actually is a simple aggregation, okay? We already know. But forget about it. Don't think in this way. You only think, okay, the result will actually be every, I mean, it's going to be every group I for using the dimension B, including its empty set, subset, on this piece of data. So basically, you can see that the result will actually be this one. It's guaranteed to be this one. Basically, it's going to be every or B equal to a particular value, and followed by the actual aggregates, and B equal to star value. Okay, that's the generic form. And you do the same thing here. It's the same thing, B equal to 1 to star, and B equal to 1 to star. So that's the, again, why I actually write using this kind of green color is because this is actually the internal output. It's really the output of this recursive call. Because this recursive call says, okay, I'm only passing these 4 tuples, but I'm only saying, okay, you only need to do dimension B. But if you think about it, if you really do the slice, essentially the A value is still here, right? The A value is just like 1, 1, 1, 1 for all of them. I actually deliberately didn't show it. But it's actually there if you do the slice. Slice is the selection, right? So A value is still there, but it's like a trivial one. So you can convince yourself that whenever you do the internal output, the A value, you can actually patch back the A value. Okay, it's still going to be 1. You can convince yourself. So that's why the actual output is that you actually append this A value to each and every internal output to produce this one. So whenever you internally you output this one from the recursive call, you actually append 1 and you actually output this one. Okay, finally you actually output this final part of output. You output this one, and then you output this one, and for this one it's the same thing. Here A is actually star, right? So that's why I call the S star slice for A equal to star. So that's why you append star here, and that's why the output of the first part, the second part, and the third part makes the entire data cube. And again, similar to our previous argument from the solution space, you can see that any tuple, if it starts with A equal to star, it is computed from this recursive call. And if it's starting from a particular value of, let's say, 1, it's actually going to be handled by the first recursive call. And if you want, you can actually look at the order they are actually computing the tuples. And look at the order we compute tuples in a plain 2-dimensional example. You will see that essentially we have 1-to-1 correspondence. Okay, I'll leave this to you to verify. Any question? Yeah, just think in almost like in this way. You start with a 3-dimensional data. You try to reduce into 2-dimensional data, where the first dimension is A equal to 1. The bottom part is the 2-dimensional data, the A equal to 2, and finally you get this one is the 2-dimensional data, the first A equal to star. Then you call the BUC on this 2-dimensional case to compute all the aggregations, and put them back, that's all the three-dimensional cube. Okay. If you are new to recursion, and this is definitely not the easy recursion, but once you get your head over it, really understand the details, it's actually very simple and very elegant. Okay. Better yet, really, if you really understand what's going on, you can actually do this for three-dimensional case. Of course, you can do four-dimensional case, but again, you will have no problem with any dimension. Okay, this is the point where you really understand what's going on. Okay, finally, let's quickly talk about the MOLAP. So that's the other solution where we don't use relational database. So again, remember that for MOLAP, essentially from the conceptual model to the logical model, they all use multidimensional model. Okay, so there is no translation or whatever needed. And finally, they implement everything using MOLAP technology, which is you need to write everything from scratch. In fact, what we are going to talk about is actually a very simple idea. The actual implementation is actually based on chunking. We didn't talk about the chunking here, but anyway. So first, people will look at the details. Why we need to consider a non-relational database implementation? Because the relational database has been shown to perform really well for all sorts of data. I mean, if you look at the history, when object-oriented programming actually become popular, people actually hypothesized that, okay, OODBMS, it's the object-oriented database, will actually overtake relational database. It didn't happen. Okay, then there are actually semi-structured data. There are whatever graph, whatever. I mean, there are different, and there are multimedia, whatever things. Initially, relational database cannot handle it, but there are things you can do to still reuse the relational database engine to handle all different sorts of demands, even spatial, for example, GIS, whatever. They are all using this kind of relational database with special indexes. For example, R3 or whatever. So MOLAP is actually especially attracting because essentially it's very small in size. You will actually see, for example. And it allows some kind of fast indexing and query processing. And not only it is small, it's also easy to do certain kind of indexing and query processing. The main problem is actually the scalability, especially the insertion. Because the insertion is actually a pen, okay? But you will see I'll quickly mention because they actually need to translate the multi-dimensional points into a one-dimensional array, and this translation actually, whenever for example, you have one more products or the year actually increased by one, this is very, very nasty to handle. There are different proposals. There are actually clever solutions to do that. So if you do it naively, it's going to be really doesn't work, okay, in practice. But there are actually clever way to do that, but it's much more complicated. Okay, we won't go into these kind of things, but just to show you the basic idea. By the way, it actually use so-called array-based multi-dimensional storage engine. So it's a mouthful to say this, but essentially, if you use a strong programming language like C or Java or whatever things, right, you can declare two-dimensional array, right? For example, in C, you can statically or dynamically declare two-dimensional array. But you should know that essentially, the address space is linear. It's only one dimension. So essentially, even if you define a three-dimensional array, for example, a matrix or a tensor, okay, essentially the compiler or you, if you do it statically, the compiler will actually do in charge of the job. If you do it by yourself, doing the dynamic allocation of space, you need to do the translation. So you need to translate the multi-dimensional address, which is in the order of I, J, K, let's say three-dimensional case, into some kind of address in one-dimensional case. Because conceptually, the memory is a one-dimensional array. Each memory cell have a number, and given a number, you can actually get it. Again, if you know pointer in C, right, that's essentially how you point to a particular location in the one-dimensional array, which is your memory. Okay, so this kind of translation actually need to be both way, right? Sometimes I mean, if think about the matrix, I mean, you can actually, for performance reason, you actually can use pointers in C programming, because every time you actually move to the next one, you only need to increase the pointer by +1, which is go by 4 bytes. This is much more efficient than, for example, doing a loop on the middle dimension, on the 3 dimension, and every time you actually have a new ij k + 1, they need to call some function to translate it to another address, which is nothing but the old address +4. Okay, if you ever do C programming, you actually do this kind of things. Pointer is a pointer to one of the elements in the matrix, and if you use a star, you actually take the value. But basically, sometimes you actually need to know this value is belong to the let's say the first row, the third column, and let's say the ninth whatever tier or whatever. Okay, so you need to do the translation both way. So here I just give you a very simple example. Again, think about this is base cubed of A and B. So you have 2 dimensions, A and B, and you have this M, right, measure. So in Rollup, if you use relational database, basically your table looks like this. Okay, so if you look at this one, I think you have 16. It's called a dense cube, which means most of the combination of the 2-dimensional values are actually present in the fact table. Okay, so basically there are 16 tuples, and each one you actually need to get a foreign key to. Again, it should be a foreign key, but I put the value there, so visually it's easy to see. So a foreign key usually takes 6 bytes or even more. So let's say it's 6 bytes, and let's say 4 bytes. So each row will actually be 12 plus 4. It will be 16 bytes, right? And you have 16. I think that you have 16 tuples, so you get 256 bytes. Again, this is a small example. But what happened is that you can actually define a mapping function to map each and every distinct values of time into 0 to 3. Okay, and map each of the item again to 0 to 3. Again, this example is exactly 4 by 4, but it doesn't matter. If you have 3 values, you just map it into 0 to 2. Okay. Then you actually use a mapping function, which is this one. You can actually think about why the function looks like this, but you can actually see that this function actually makes sure, first of all, it's a one-to-one mapping both way. So in other words, given a particular time and the item within these 4 values on each dimension, you can get a unique number on the right, which is the address. And given an address, you can always get a unique time and item index or number. Okay? So again, this kind of uniqueness definitely helps us. I mean, we don't really want to have an ambiguous addressing system. And also, this is actually very compact. There is no waste in the address. Okay? But the second part is actually not really the most important thing, because in practice, sometimes you would like to leave some room just for future updates. Okay? But anyway, I mean, so what you do is that you have 0, 0. I mean, first after mapping, the first tuple becomes 0, 0, 6, 0, 5. Okay, this already saved a little bit. This is like a 4 bytes, right? I mean, presumably you can do that. But the more interesting thing is that you can do the translation, and this actually becomes 0. So this is actually, I call the offset or the address. It should be the offset because you actually, because address 0, I mean, it's not really the physical memories or logical space you put it on the 0. It's actually starting from some anchor point. Then relative to that, you actually, the first entry is going to be whatever. So that's why it's more like offset. So once you get these 2 guys, right, you can reorder it using the offset. So this actually will become like this on this table, right? And you can see that this table is dense, which means everything is so every offset from 0 to 15, which is 16 different slots, each slot actually have a value. And if you know C, we do not need to store these kind of things. All we need is actually this one, because we only need to remember where the beginning is. And if I'm looking at this cell value, I can work out the difference between them and know that this one is the 5th entry. From the 5th entry, you can work out what is the item, what is the time. Okay? It should be both be, I think, 1, 1 or something. Yeah, it should be 1, 1, right? It's only 1 times 4 plus 1 equal to 5. There is no other 2 combinations which give you 5. Okay? So in other words, now, what's your space requirement? Each one is just 4 bytes. And this is 4 times 16, right? This is 64 bytes. And in this case, it's the lower bound, right? Because you have 16 different measure values. Each value takes 4 bytes to store. Now I'm actually using the bare minimum to do that. So you can immediately see that this is only 2 dimension. So if it's 10-dimensional cube, again, this is the fact table, right? Essentially the fact table. Even it's 1 billion value, right? I only need to remember 1 billion measure value, assuming only 1 measure. Okay, 2 measure, then twice of that. Compared to the relational storage, where for each tuple you also need to include 10 foreign key, which takes at least 60 bytes, right? It's a huge overhead. So you can imagine that even with 1 billion, let's say, numbers, let's say 1 billion times 4 is only 4 billion. 4 billion is about 4 gigabytes, right? 4 billion bytes is, yeah, because billion is 10 to the 12. Megabytes is, yeah, anyway, I mean, so basically it's still doable, okay? So you can see that the space is really small. And that's it. Okay, so this is for the so-called dense case where there is no empty space. But just imagine that the original data cube, 2-dimensional cube, only have 2 tuples. I just remove everything in between. Okay, that's the same one, but remove everything in between. Again, actually, if it's only 2, you don't need to map into 4 values. But I'm not changing anything, so just pretend that we really have something like this. Then you do the same thing. You end up with this guy, right? This guy, you can actually choose to use the original one, but essentially everything here is actually wasted. But you still need to keep, so the value stored there doesn't matter. Okay, it's just like uninitialized in an array, but you have to keep it there because otherwise you can't decode the time and the item for the last entry correctly. Okay, you see, you actually have a big hole. Okay, this is actually not too bad. It's a continuous hole, but anyway, you are wasting space. So in this case, you can actually work out that you can actually use so-called sparse representation, which is actually record the offset and this address, offset and measure value. So this is going to be assume that the offset can be recorded in 8 bytes. It's going to be 8 plus 4 times 2, right? So it's going to be 24 bytes. But if you do something like this here, it's like 4 times 16 is 64 bytes. So this one actually wins. So for sparse case, you can actually use, this is called a sparse array. That's actually by default, they have to use sparse array because not every, actually, especially in the fact table, it's definitely not dense. You can actually think about why it's definitely not dense. Basically, sparse is actually more common, and they actually also use another thing called chunking together with the sparse array. So basically, this essentially reduces the storage, but makes implementation really, really hard to do. And this is actually a static case. You also need to deal with the dynamic case, which is even harder. But it's doable, okay. So nowadays, actually, one common trend is that we don't entirely go to relational. We don't entirely go to multidimensional. So we actually do it in a hybrid way. Okay, try to take the best out of both worlds. So what's happening is that for the base qubit, you use the relational which is essentially the fact table. Okay, the base qubit is like ABC, right? For ABC, you actually use the relational table. This is easy to do. Also do ETL, do the loading, because whenever you do the updates, you can directly insert into the fact table. Then all the aggregates, let's say the qubit of A or the qubit of BC, they are actually aggregated from this one, and they are actually stored in multidimensional format. Because usually, whenever you do the aggregation, the smaller qubit tends to become denser and denser, and it makes much more great saving to use a multidimensional thing. But of course, I mean, you can say, okay, for BC, I still relational format. It's okay, But in general, you can use multidimensional sparse array or dense array to store the highly aggregated qubits. So the real system can be accommodating both of them. Okay, so that's all for the data warehouse, and yeah, we don't have time for the clustering part. Maybe I just explain what's going on. So usually we actually move on to the classification or other parts, but our project will actually be related to clustering. It's not too much related to clustering, but I think just for the sake of safety, we actually talk about clustering first. So starting from next week, we're going through the clustering part, and we also have additional things to quickly talk about the project. It's going to this project give you another way to think about, okay, the clustering can be used in other ways. Okay, essentially in multimedia retrieval, whatever, that there is a place for this kind of method to be used. So that's the plan. And then after the clustering, we are going to go back to the classification part. Okay, so I guess that's all for today, and I'll see you next week. Which one?
The last slide.
You mean the... Oh, okay. D is usually dimension. Sorry, I'll close it. D is usually the dimension.
Yeah, I have it open.
Yeah.
So you had given an example.
Yeah.
In that it was... So in this,
yeah.
What is D and N?
Here, first of all, N is the number of tuples. So in this case, N equal to 2. D is the dimension. Dimension is actually, here is actually 2.
Here it is.
Here is actually 1. Sorry, no, sorry. The D actually need to look at the original one. Look at this one. It's actually 2. There are 2 dimensions.
Okay.
2 dimensions. So you should, I mean, think about, as I said, I mean, this is a 2-dimensional cube grid.